Okay, so last section we're going to look at this week is 7.4. The plan right now is, as long as tomorrow is a normal day, all I have planned is a review. We'll just be reviewing this stuff again. I've got a worksheet. You can kind of work in groups and help each other, and then we go over it. If we don't, then we're going to end up losing that review day. If we have a delay, we would have a shortened class, although you guys are period 5, 6, so then they can't mess with the lunches. So no, we would actually have a normal class tomorrow if there was a delay. So we'd have the same amount of time to review. Okay. If there's no class tomorrow, we will just have the test on Friday.
Do you have the worksheet printed out today?
I did not print it yet. I have it. You could take a picture of it if you want to see it. But no, I did not. I did not print it yet. All right, so we're going to be working with trig identities. Okay, there are hundreds of trig identities. In this class, there are about 10 that you need to know. Even I don't know all the trig identities. Mr. Babb asked me one yesterday, and I couldn't remember it off the top of my head because it's not one of the basic identities. I remember the basic ones, but if I need a more advanced one, what I do is I just look it up. So that's because there's hundreds of them, you can't remember them all. So an identity, it's basically a formula, it's an equation that is true for all values of the variable. Okay. So here is what we would call an algebraic identity. If I had somebody solve that equation in Algebra 1, what you would end up with is the same thing on the left and on the right. 2x plus 3 equals 2x plus 3. So when you end up with that, 2x plus 3 equals 2x plus 3, you could subtract 2x from each side and all the letters are gone and you have 3 equals 3. What that means is this equation is true no matter what value of x you plug in. Plug in 5, it'll work. Plug in negative 17.4, it'll work. Because what's on the left and on the right are the same. That's an algebraic identity. What we're going to be looking at are trig identities. Formulas that have trig in them that always work. Doesn't matter what angle you plug into the formula. It works for any angle. Just like this equation works for any number. So you should be familiar with, bless you, the basic, some of these basic identities. Like the reciprocal ones, you guys already know those. Okay? Because we don't have a way to type cosecant in on the calculator. We have to take the sign and flip it. We don't have a way to type in secant. We take the cosine and we flip it. But we don't have a way to type in cotangent. We have to do 1 divided by tangent. So we've been using these ones all along on the bottom. The top ones we don't use as much, but this one and this one are repeats of each other. They're repeats. If you think that this one and this one are different, then that's like saying this and this are different. No, it's the same formula. All you've done is you've just moved some things around a little bit. Okay? Moving things around doesn't give you a new formula. It gives you the same formula with stuff moved around. Okay? Like that. Same thing here. This top one and this bottom one are the same thing, just moved around, and those last two. Okay, so those are called your reciprocal identities. Okay. The next group we call the tangent and cotangent. There's 2 of them. And those ones basically say that if you take sine and divide by cosine, you get tangent. It's one of them. Or if you flip it, cosine divided by sine gives you cotangent. Now, the last group are what we call Pythagorean identities. And the reason they're called Pythagorean identities is because they have a format that looks kind of like something squared plus something squared equals something. And that's the 3 of them. And these 3 groups, reciprocal, quotient, Pythagorean, make up what we call the fundamental trig identities. So any class you take about trig identities, those are the basic ones you're always going to learn. And that after a while of using them, most people have these ones memorized. I have these memorized. And a couple others. But beyond that, most other identities, we usually look them up in a book when we need them. Okay, so the first one at the bottom says sine squared plus cosine squared equals 1. The second one says 1 plus tangent squared equals secant squared. And the third one is 1 plus cotangent squared equals cosecant squared. Now, with these identities, you might see them rearranged. I'm going to take this one. So sine squared plus cosine squared equals 1. And I'm going to show you how you can write it differently, but it's still the same identity. I'm going to subtract sine squared from the left and from the right. All I did was subtract the same thing from both sides. When I do that, this is gone. And now I have this. Cosine squared equals 1 minus sine squared. That's the same Pythagorean identity as this one. All you've done is move something to the other side. So sometimes that's a little bit tricky because you have to look for something you know, but rearranged a little bit. Okay? Same thing with any of these. You could take the 1 and subtract it to the other side. You could take tangent squared and put it on the other side. There's basically 3 ways to write any of those, moving stuff around. Any question on why what's in this box and this box are the same thing? Okay. Let's take a look at this one for a second. It says tangent equals sine over cosine. Well, let's look at this. Tangent squared. When you square something, can somebody tell, like, what does that mean? Like, if somebody didn't understand what this 2 up high meant, how could you tell them a different way to write tangent to the second power? Yeah?
Multiply by itself.
Yeah. It's tangent times tangent. Well, now look up above and see what tangent is. Tangent is sine over cosine. Sine over cosine. Sine over cosine. What do you think sine times sine is? Yep. Yep, sine squared. And what about cosine times cosine? Yep. Cosine squared. So, point here, tan squared is sine squared over cosine squared. What do you think tan cubed would be? No, kind of just following this pattern.
Oh.
So tangent was sine over cosine. Tangent squared was sine squared over cosine squared.
Sine cubed over cosine cubed.
Yeah. So these formulas, you can use them with higher powers. If you had tangent to the 20th, you could have sine to the 20th over cosine to the 20th. We would never have one that high, but you could. You could do the same thing with these. Let's take a look at, I'll just show you this one, cosecant. Cosecant is 1 over sine. I'm going to do exactly the same thing I just did with tangent. Cosecant squared. How could you write cosecant squared if somebody didn't understand what this 2 meant? Just get rid of that 2. That's all I want to do.
Cosecant times cosecant.
Hey, it's cosecant times cosecant. Well, cosecant is 1 over sine. Cosecant is 1 over sine. Multiply them together. Brandon, 1 times 1? 1. And Eric, sine times sine?
Sine squared.
Sine squared. So cosecant squared is 1 over sine squared. Cosecant cubed, 1 over sine cubed. Cosecant to the 5th, 1 over sine to the 5th. Right? So the 2 that I put asterisks next to, those you can use with higher powers. The Pythagorean ones you cannot. You can rearrange them, but you cannot use them with higher powers. Okay? Those are pretty much what they are. That's it. All right. So I already talked to you a little bit about why trig identities would be used. Whenever you're deriving or integrating something, usually you end up with an expression that can be simplified in some way. If you can simplify it, it makes calculus easier to do. If you don't know how to simplify it, it's going to make it very difficult. So that's the application of trig identities would be in the next math class you would take. So there's a few different tricks that you can use to simplify an equation that looks complicated with trig identities. One trick is to use the 3 groups of formulas I just showed you to change everything to sine and cosine. That's one trick. So we're going to take everything in the problem that's not a sine or a cosine and make it a sine or a cosine. If it already is a sine or cosine, leave it. You don't have to touch it. And there's 2 other kind of, I call this is like a trick. It's like a big idea, one way to start the whole problem. Okay, there's 2 other ones that we'll look at. Okay, let's look at this. Cotangent divided by cosecant. That's kind of a complicated expression. It's got 2 different trig functions and division. We're going to see if we can reduce that somehow to something simpler. And then if we were doing calculus, we would use the simpler version to do the next step. So let's start with cotangent. Can someone tell me, using the table of identities I just gave you, how you can rewrite cotangent using sines and cosines? This is basically, it's all substitution. That's all that this is. Jared?
Cosine over sine.
Yes. Cosine over sine. How about cosecant? How can we write cosecant using sines and cosines? Chris?
1 over sine.
1 over sine. Now, all the rules you know about arithmetic with fractions apply here. If I wanted to divide 2/3 by 4/7, how do you divide 2 fractions?
That equal,
Okay, what do you do at the top? Take the top, keep it the same, multiply by the reciprocal of the bottom. We're going to do exactly the same here. Keep the top the same. What's the reciprocal of what's in the bottom? Brianna? Sine theta over 1. Now, multiply those together. What's going to happen when we multiply those 2 fractions together? Yeah?
Cancel out the sine.
Yep. Just like multiplying 2/3 times 3 over 1. If you've got the same thing in the top and the bottom, it cancels. So, that's gone. That's gone. And now we have cosine theta divided by 1. Do I need to put divided by 1? That doesn't matter. So, if you wanted to take the cotangent of an angle, any angle you want, doesn't matter, and divide by the cosecant of that angle, it's exactly the same as if you had just taken the cosine. Much, much simpler formula than what we started. Okay. Any questions on them? Okay, that would be considered an easy one, okay? Because you could basically do it in 2 steps. Write it as sines and cosines, and then multiply by the reciprocal, and then you're done. Okay. Let's look at this one. This would also be considered another easy one. I wouldn't say we do any that are extremely hard, but we do some that get a little harder than this. Okay, so let's use the trick, the only trick that we know, which is to change to sines and cosines. So, Kira, what is cosecant if we rewrite it as sines and cosines?
1 over sine.
Yep, it's 1 over sine. Times, Kaya, what is tangent in terms of sine and cosine? So we won't be using those, we want to use just the formulas that I gave you at the beginning. Just those, we won't use those adjacent opposite words today. Want to help her out? What's tangent? Yeah, make here. Sine over cosine. Now you're basically at the same step you were at in the last problem, except you don't even have a fraction over a fraction. So when I multiply here, what happens? Sure?
You just get 1 over cosine because the signs cancel.
Sines cancel. Get 1 over cosine. Now the question could go through your head, should you stop there? Maybe, but I think if you can write something so that it's not a fraction, that is simpler than having a fraction. So what is 1 over cosine? The same as. Yep, secant. So if you had a problem that required you to take the cosecant of an angle and multiply it by the tangent of an angle, you could do the same thing a lot simpler by just taking the secant, and you get exactly the same answer. Questions on that? Okay. So, there's really 2 types of problems you can have. These are simplifies. The thing that I don't like about a simplify is it's open-ended. They give you a problem, and you just keep going till you think you're done. That's a simplify. This kind of problem is a verify. Verify means, here's what you should start with. When you're done, here's the answer you're going to get, so you know when you're done. When you take the right-hand side and do enough stuff to it so it turns into the simple-looking side, then you know you're done. Right? So, again, simplify, you just keep going till you think you're done. You don't really know where to stop. All right? So, the approach that we're going to take with a verify is you want to get each side to look exactly the same. You always want to start with the more complicated side. Always. It's a lot easier to take something that looks complicated and simplify it than to take something that's simple and complicate it. So when you have a verify, you should be able to look at it pretty quickly and tell which side is more complicated. It should be usually pretty clear. So you always want to work with the side that looks more complicated to make it look like the simpler side. That's the goal. Now, you can work with both sides at the same time. I'm not going to do that. I'm going to pick one side. I'm just going to mess with that side. I'm going to leave the other side alone. Working with both sides at the same time can get confusing. Okay. So that's just explaining the difference between the 2 types of directions you might see. Simplify versus verify. Okay. So our first trick we had was to change everything to what? Yeah? Cosine and sine. Our second trick we're going to look at is to rewrite things with a common denominator. Now, remember, common denominators are used anytime you want to add fractions and they don't have the same denominator. Add or subtract. What I'm going to do is I'm just going to put these in different colors. So remember, to find a common denominator, all you have to do is multiply each fraction by the other denominator. So this one would get multiplied by 4 over 4. This one by 3 over 3. That will always give you a common denominator. So that would give me a common denominator now of 12 in each fraction. We're going to be doing the same thing, except we're going to do it with trig. The idea is still the same. Multiply each fraction by the other denominator, and that gives you a common denominator. Questions on that idea? That's how you do it with numbers. All right. So when you first look at this problem, you might think that that trick doesn't even apply, common denominators, because there's no fractions in it. Well, you might have fractions by the time you're done. We'll see. Okay, so this one says sine, and then in parentheses, cotangent plus tangent. Now, there's a property that we can use with numbers when you have something on the outside of parentheses. Jacob, do you remember what that property is when you have something on the outside of parentheses and you do something with it to what's on the inside? Distributive. You can do the same thing here. Yeah, very good. We can do distributive property. Now, you might then say, well, shouldn't we change to sines and cosines? Because you taught us that too. You're going to have to do both. You're going to have to change that to sines and cosines, and you're going to have to distribute. What order you do that in doesn't. So I'm going to distribute first. So when I distribute, all I have is sine times cotangent. It's the first part. And the second part, bring down my plus, sine times tangent. Now let's change everything to sines and cosines and see what happens. So we're going to end up with fractions when we do that. So I'm going to make everything here a fraction. So let's start with this one. Just make it sine over 1. Sam, what is cotangent in terms of sine and cosine? I know it's 1 over tangent, but that won't help.
Cosine over
Cosine over sine plus, we're going to make that sine over 1 times, what is tangent? Chris?
Sine over cosine.
Yep, sine over cosine. Okay, a couple important things here. You can never cancel out a numerator and denominator across a plus sign. You cannot do that. No way. That's totally wrong. Okay. The only time you can cancel the top and the bottom is if there's a multiplication between the fractions. If there's a plus or a minus sign, think of that as a wall. You can't go across it. So, knowing that, is there anything here that does cancel? Yeah. Yeah, that and that cancels out fine. And all you're left with is cosine over 1 plus. Now let's multiply straight across on the right. What's sine times sine? Sine squared over 1 times cosine? Cosine. Now, whenever I see sine squared, okay, we're not there yet, but I'm starting to think about this. Because that has a sine squared in it. Okay? So if I get a cosine squared to pop up somewhere, then I know I should definitely be thinking about this one. Okay? But I have a sine squared right now. Let's see if cosine squared pops up with it in a second. Okay, so we've changed everything to sines and cosines, so that trick is done. What's my next trick that I could use here that we just learned? Yeah. Common denominator. Yes. So now we're going to find a common denominator. What's going to be my common denominator here?
Cosine.
It's cosine. You just take the two denominators you have and multiply them together. That's your common denominator. So the part on the right is fine. It already has a denominator of cosine. I mean, I guess you could multiply the top and the bottom by the 1, but that's not going to do anything. What do we have to multiply top and bottom by on the left? Cosine. You multiply that fraction by the other denominator. That's what I just showed you with the numbers. Cosine, cosine. Cosine times 1, we already have that in the bottom. What's cosine times cosine? Yep. Cosine squared. Now, we've changed everything to sines and cosines. We found a common denominator. There's nothing else you can do other than now you have to recognize something that's there as one of the identities I originally gave you. Cosine squared plus sine squared. Does anybody recognize that one?
It's equal to 1.
It's equal to 1. This says sine squared plus cosine squared. That's the same thing as cosine squared plus sine squared. It's like 2 plus 1, 1 plus 2. Same thing. So cosine squared plus sine squared, what did you just say? It's equal to what? 1. So this entire numerator turns into the number 1. And lastly, what is 1 divided by cosine?
Yeah.
So look at how complicated of a thing we started with. 3 different trig functions with addition and a distributive property. And all of that, when you get it out, is the same as just doing the secant. So if I had to do calculus with this thing right here, that's going to be complicated because there's a lot going on. But if I had to do the next step in calculus with this, that's a lot easier. And it's equivalent to what I started with. Okay. Questions on that? Okay. Let's take a look at this one. Start first, verify. So now, verify, you first want to look at the side that looks more complicated. Which side looks more complicated? Yeah,
The right.
the right. So we're going to work with the right-hand side. Our goal is to keep working with the right-hand side until you get sine. When you get sine, then you know you're done. So let's just copy over the right-hand side. Secant over tangent plus cotangent. Okay, what's one thing that I could try first on that right-hand side? So far, I've only shown you two things to try right at the beginning.
Change it to sine and cosine.
Sure. Let's try changing everything to sines and cosines. I will tell you, a lot of these identities, they're going to look a lot worse before they start simplifying. Even this last one. To me, the second step looks even worse than the first step. But if you keep going, it eventually will simplify. So let's start with secant. Emily, what's secant? Okay. 1 divided by cosine, which doesn't really have a lot going on with it in the top. There's more stuff going on in the bottom. So the bottom is probably what I'm going to focus on first, right? Because we have addition. Maybe I can do something with that addition. Okay, but the top, it's just a fraction. I can't really do much with it right now because there's nothing else next to it. Let's do tangent. What's tangent? Sine divided by cosine, and cotangent, cosine, divided by sine. Okay, so we've changed everything to sines and cosines. That trick's done. What else could I do here, especially in the bottom? Yeah.
You can cross opposite.
What did I say about canceling across a plus sign? Can't do it, right? Think of that plus sign as like a wall.
I did see that.
So yeah, if that was multiplication, then yes, everything in the bottom would cancel out and become 1. But it's addition, so we got to do something else, which it's harder than multiplication. Yeah.
Like combine them all, so sine plus cosine over cosine plus sine.
Well, what are you doing with the two fractions? You're trying to do what with them? You said combine, but I'm just combine how?
Add.
You're trying to add them. So what's the rule when you want to add fractions together? Yeah, have to have a common denominator. So the common denominator is going to be cosine sine. It's always the product of the two that you have. So the top, it's just going to stay as 1 over cosine, probably till the very last step in this problem. All right. So what would I end up so this is my common denominator. Let me write this first. Sine times cosine. What would I end up multiplying the fraction on the right by? What over what? Look at what it's missing to have the common denominator. Yeah, it's missing cosine. So we're going to multiply by cosine over cosine. And what's the fraction on the left missing to have the common denominator? Chris?
Sine over cosine.
You have to multiply top and bottom by the same thing. Gotta be Nikira? Sine over sine. Because if you multiply by sine over sine, now this fraction has sine cosine in the bottom. This fraction has sine cosine in the bottom. Now they have the same denominator. We just have to do that out. What's sine times sine? Sine squared plus, what's cosine times cosine? Cosine squared. So now, as far as tricks go, you've used them all. You've changed to sines and cosines, you found common denominators. Now you just have to simplify this as much as you can. Does anybody see something there that simplifies? Yeah? Yeah, what is all of this equal to? 1. That's a Pythagorean identity. So now, you have this. You have a fraction divided by a fraction. 1 over cosine divided by 1 over sine cosine. How, we've had this, I think it was the first problem I did with you guys. How do you divide a fraction by a fraction? Yeah.
Multiply the reciprocal by, multiply by the reciprocal of, in this case, the denominator.
Always the denominator.
Yeah.
Yeah. Keep the top the same, multiply by the reciprocal of the denominator. Okay. What's going to happen when you multiply these two fractions together? The cosine would cancel out. The ones would cancel out. And what are you left with? Sine. So you're left with sine. That's as simple as you could get it. Scroll back up and see if that's what they told you were supposed to get. Yes, it was. So we just proved that what's on the right turns into sine. So in this kind of problem, I'm not really looking for the answer. I already know the answer. The answer was sine. We knew that all along. What I'm looking for is why. Show me the steps how. Now, so far, most of the identities I've given you have been pretty straightforward. Okay? I would say most people that would do these problems would probably do it pretty much the same way. When you start getting into more complicated identities, there's many ways to do it. The goal is to try to find the shortest one. But sometimes you start an identity problem and you get to like 5, 6, 7 steps in and it's just getting worse and worse and worse. If you find that that's happening, one of two things. You either made a mistake and something that should have canceled out didn't cancel out, so now it's messing you up. Or the approach that you started with, although it may work eventually, it's a very long way to do the problem. So you might want to start and try something else. If you tried distributive property first, just try changing to sines and cosines first. Try it a different way. All right, so the third trick that we're going to look at is to multiply the top and the bottom of a fraction by the conjugate. We saw conjugates come up when we divided complex numbers. This has nothing to do with complex numbers, but the trick we're going to use here is a trick we've used before. So if you had something like sine theta plus 1, the conjugate is sine theta minus 1. I'm not going to put an equal sign between them because they're not equal, but it's just that's the conjugate. So the conjugate is when you just change the plus or the minus sign to the opposite. Change the sign in the middle to its opposite. It's going to be very obvious when you need to use this trick. You'll see. Right? So now we got 3 tricks. Try changing to sines and cosines. Try common denominators. Try multiplying top and bottom by the conjugate. Okay. This is a problem that when I look at it right away, it's just like screaming at me conjugate. Because I see 1 minus a trig function. And then on the other side, 1 plus a trig function. So this problem is going to have something to do with conjugates. Now, I said to you, when you look at a verify, it's usually pretty clear which side is more complicated. I don't think that's true here. I think both sides pretty much look the same in terms of complexity. No question here, the right-hand side is way more complicated. Here, though, each side is a fraction. One part of the fraction has 2 things in it. The other part of the fraction has 1 thing in it. Same thing on each side. So it does not really matter which side you start with. Unfortunately, the end result doesn't really simplify that much more than the beginning result. Not really. So we get to pick. Do you want to start with the left-hand side or the right-hand side? The right? Okay. So, right-hand side. 1 plus sine over cosine. Let's run through all the tricks we know so far. Should we try changing everything to sines and cosines there? Why not? It already is sines and cosines. So that trick isn't going to do anything. Should we try writing it with a common denominator? Why?
Because you're not dividing by a fraction.
Dividing wouldn't have anything to do with common denominators.
You're not adding.
You're not adding fractions. If you look at this, this is only a fraction. There's not 2 of them. If you had 2 of them that are separate and you wanted to combine them, then that might be a common denominator. So, what's the third trick that I just mentioned? Brandon?
Multiply by the conjugate.
Okay, multiply by the conjugate. What's the conjugate here? Yeah. So it's going to be kind of like that. So what do you think? What do you think the conjugate is? no, not negative 1.
Sine minus 1. Or would it be 1 minus sine?
1 minus sine. Conjugate is when you change the sign.
Oh.
If it's a plus sign, we make it a minus. So 1 minus sine. And 1 minus sine. Now, when you multiply by a conjugate, always multiply the conjugates together before you do anything else. Because multiplying conjugates together is going to cancel out something. Don't even do the bottom. You might be thinking, well, maybe I should distribute this cosine out. No, don't. Just leave it. Okay. When you have conjugates, multiply them together first. And what's going to end up happening is it's going to cancel something that's in the bottom. So you're not even ever going to have to worry about distributive anyway. Okay. But you wouldn't know that till you do one of these problems. But now I'm telling you. Always multiply the conjugates first. So we're going to leave the bottom exactly the way it is. The other thing I like about the bottom is we're dealing with the right-hand side. We just introduced a 1 minus sign into the bottom. That's exactly what's on the left-hand side. So don't mess that up. You already got part of what you want. Okay? We just have to FOIL the top and see what the rest is. So cosine, 1 minus sine, I should put a t in there. And now FOIL the top. 1 times 1 will give me 1. 1 times negative sign. 1 times positive sign. Sign. Those cancel. Whenever you multiply conjugates, the outer and the inner always cancel. 1 times negative sign, 1 times positive sign. Gone. So all you need to worry about with conjugates is the first and the last. We did the first, 1 times 1, and now the last. What's positive sign times negative sign?
Negative sign?
A positive times a negative is a negative, but negative sine squared. Now, there's something there to recognize. Okay. So, make sure you have that written down and go back to the identities. And see if you recognize something there as an identity. What do we have in the top of our fraction right now?
Sine squared. 1 minus sine squared.
1 minus sine squared. Okay. Is that equal to anything?
The first identity.
Okay, so something about the first identity you can use to help you. So the first identity says sine squared plus cosine squared equals 1. That's not exactly what we have. But, yeah.
That's equal to cosine squared.
Right. 1 minus sine squared equals cosine squared. So let's write that down. So now 1 minus sine squared turns into cosine squared. Keep the bottom exactly the same. Okay. What do the top and the bottom both have in common there?
Cosine?
How many?
1.
They each have 1 in common. So you can cross out 1 from here and 1 from here, and you're left with cosine divided by 1 minus sine. Let's go back up and see if that's what the left-hand side was. Cosine divided by 1 minus sine. Perfect. Okay. So any question on it? So unfortunately, the end result isn't really that much simpler than what you started with. All you've really done is kind of rearrange it, but it's not like this one where we canceled out a lot of trig and made it really simple.
I have a question.
No.
Why would anyone ever need to verify a trig identity?
They should be able to answer that based on what I told you. What did I tell you?
Like, what's the point of learning this as a topic?
Check your
What did I tell you? I wish I had instant playback.
Did it happen like literally in this lecture?
Yeah, I told him like 3 times while you do it.
I'll be back in like 5 minutes.
To make the expression easier.
To make it easier. Okay, so
To
what would be
deal
the
with.
application?
I'll be back.
To deal with
Where would you be dealing with it?
on a calculator. Or
No calculators at all for this stuff. You even have something right on the board over there that I referenced.
oh, derivative.
Yeah, I told you if you had to take a derivative of something, which is calculus, you can't do it unless you know how to simplify trig identities. So when Mr. Bab comes back, make me look good, like I told you. A bunch of. I'm not going to go through all of them. Let's try this one. Okay, this is another one where it's a little tricky, and I remember how to do it because I taught it the week before, and I started out doing it the wrong way. I started out changing everything to sines and cosines. But changing to sines and cosines in this problem is an awful idea. We're going to change to tangents, and you'll see what happens. So, any thoughts for Mr. Bab? Yeah?
Make dealing with derivatives easier.
Yeah. Could make dealing with derivatives, or what else did I say easier? Remember the other one? What are derivatives? That's one, and then the other opposite of that is in an integral. Makes that easier too.
What course do those have?
I don't know. Do you guys know?
I'll give you a hint. It's the successor of the course you're currently in.
Calculus.
I did tell them.
I
It's on tape.
I just have bad memory.
That's okay. All right, thank you.
Have a good one.
So, yes, changing to sines and cosines here, although it'll work eventually, just like driving to California by heading to Boston will work eventually, but it's really not the best way to go about it. So what we're going to do is start with the right-hand side, and we're going to change everything to tangents. Now, that's not something that I gave you as one of the 3 tricks, but when we do trig identities, it's kind of like a chess game, right? Somebody may teach you, certain moves that this is a good move to do, this is a good move to do, but you can't just say just do this move all the time and you'll just win. Well, no, you got to kind of look at the board, look at the situation, and you got to react to what you see. So that's what I'm kind of doing here. I'm reacting to what I see. I see a lot of tangents on the left. I don't see any sines and cosines on the left at all. So changing to sines and cosines on the right might not get me what I need in the quickest way. But I do see tangents. Okay, lots of tangents. So let's try changing everything to tangent on the right and see what happens. So the first one is already tangent. So we're going to leave that alone. How about cotangent? How can you write, if you had to graph cotangent, what would you type in on the calculator? Yep. 1 over tangent. And the bottom is exactly the same, except it's plus. Tangent plus 1 over tangent. Now, if you have something like that, let's say I had, you don't have to write this part, I just want to show you with numbers. 3 minus 4 over 3 plus 4. Let's say I double everything. Double everything there. And I put 6 minus 8 over 6 plus 8. When I doubled everything, did I still get the same? Like if you simplified that and simplified that, would you get the same thing? Yeah. This is negative 1 over 3 plus 4 is 7. This is 6 minus 8 is negative 2. 6 plus 8 is 14. Reduce that fraction, it's negative 1/7. So you can multiply everything here by the same thing, and it doesn't mess it up. So that's what we're going to try to do. I want to try to force this to be what it should be. It's supposed to be a tangent squared. So what would I have to multiply what I just circled? What would you have to multiply it by to make it tangent squared? Yep. Tangent, but you can't just do it there. You have to do it everywhere. So it's okay to do that. Just like when I doubled, I did it in all 4 spots. So let's multiply by tangent in all 4 spots. Okay? So that's going to give me tangent squared minus, what do you get if you multiply 1 divided by tangent times tangent? We just did the first one. That was tangent squared. Yeah?
Would that be like 1 over tangent in parentheses squared?
Well, it would be like that. 1 over tangent times tangent over 1.
Oh, you get tangent over tangent.
Tangent over tangent, which is what?
1.
Exactly what we wanted to happen. So the top is perfect. Now let's do the bottom. Multiply this by tangent. Okay, we're just trying to multiply everything by tangent because we noticed that it would make the top tangent squared, and that's what we wanted. Okay. So Chris, what's tangent times tangent? Tangent squared. And Eric, 1 over tangent times tangent?
Tangent over tangent.
Which is?
Tangent squared.
No. Tangent divided by tangent, it's like 5 divided by 5. You're dividing 2 things that are the same.
Oh,
1. So, that's our right-hand side now. The top looks good. That's exactly what we want. The bottom, does the bottom look like what we want? No. Tangent squared plus 1. Let's go back in our notes and look that up. Tangent squared plus 1. Anybody see formula up there that would help us with tangent squared plus 1? Chris?
Yeah, the 1 plus tangent square equals sec squared. That one.
Tangent squared plus 1 equals secant squared. That's a Pythagorean identity. I know ours says tangent squared plus 1, but that's the same as 1 plus tangent squared. It's like 5 plus 2, 2 plus 5. It's the same thing. So 1 plus tangent squared equals secant squared. So let's go back to our problem. All of that turns into secant squared. So tangent squared minus 1 over secant squared, and that's exactly what we were supposed to get. Okay? So by changing to sines and cosines, it wasn't actually that bad of a problem. This is all the work for the problem right here. It's like 3 steps. Multiply everything by tangent, use a Pythagorean, actually 2 steps. Multiply by tangent, use a Pythagorean identity, and you're done. The hard part would be is if you didn't notice to multiply by tangent, then you might get stuck on this problem for a half hour. If you find the right way to do it, you're done it in like 2 minutes. But it takes a lot of practice to find the right way to do it. Okay, so I'm probably making a lot of them look like they're quick. You could try some of these same problems on your own and you get stuck for an hour. If you get stuck for an hour on one problem, I would say move on, even if you get stuck for more than 10 minutes. Because if you're stuck, you're not thinking, you're just not in the right mindset to get that problem. Maybe try a different one and you'll get that one. And then that'll spark something to say, oh, well, yeah, maybe I'll try something like this now. Okay. I think that's good. Okay, so those are the problems for tonight. Okay, not a ton of problems. It's 4 through 8, 11, 12, 21 to 22, and 25 through 27. So the plan is we're done all the material for the week. If we have any kind of class tomorrow, we will have a review where we practice more of these. If we don't have class tomorrow, then we'll end up just having a test on Friday.